All right, so this is group 3 for section 8 in Stat512. This is Sabrina Dopp and Michael DeLucia, and our final project is on the COVID-19 vaccine in statistics. So we're going to start with our background and our research questions, then we're going to dig into our modeling, and finally we're going to see what results that we can conclude from our data. So first, the background and our research question. On December 11th, 2020, Pfizer released the first COVID-19 vaccine. This was the first FDA authorized vaccine in the United States. And as of October 13th, 2021, there have been over 200 million full vaccines administered and almost 500 million total doses administered in the United States. The release of the vaccine was expected to slow the spread of the virus and to alleviate symptoms for those who did contract the virus. And since the pandemic first started, there have been almost 45 million COVID cases in the United States. So vaccinations were made available to those in different age groups. As more vaccines were produced, it was given to the most vulnerable first, and then given to younger people who generally were at lower risk of the disease. And a full list of the vaccine rates by age range and state can be found at mayoclinic.org, who got their data from cdc.gov, which is where we sourced our data from. So our general research question is, what is the correlation between the COVID-19 national vaccination rates to the population demographics? So question 1, we wanted to see if age group had a linear impact on the vaccination rate over time, with our X2 being the age group, with our X1 being the date administered, and our Y variable being the amount of people fully vaccinated in the United States. Our question 2 is, does the number of new COVID-19 cases have a linear impact on the vaccination rate over time, X3 being the number of cases? Our third question is, does the number of new COVID-19 related deaths have a linear impact on the vaccination rate over time, X4 being the number of deaths? And question 4 is, does the number of people currently hospitalized for COVID-19 have a linear impact on the vaccination rate over time, with our X5 being the number hospitalized? So for our variables, we had beta 1 be the linear impact of date on the national vaccination rate. Beta 2 is the linear impact of age on the national vaccination rate, with our beta 6 being the impact of date times the age. Beta 3 is the number of new cases on the vaccination rate. Beta 5 is the impact of current hospitalization, and our beta 4 is the impact of the number of new COVID deaths on the national vaccination rate. So we're going to go ahead and get into our modeling. Our first model started off extremely well. As we can see, all of our p-values are, sorry, I have to go back. All of our p-values in our summary are very low. Almost all of them at 2 times 10 to the negative 16th, which is an extremely low p-value, showing that we started with a good model to begin with, and this is further backed up by our R squared starting at 0.9485 and our adjusted R squared starting at 0.9482, with our F statistic being 2,986. Although for the Brown and Shapiro tests, we did run into some problems. The Brown Forsyth test gave a p-value of 1.27 times 10 to the negative 29th, which means we do indeed have a non-constant variance, and so we tried to model for that. And our Shapiro-Wilk gave a p-value of 2.2 times 10 to the negative 16th, which also is something that we tried to account for in our revised models. The Shapiro-Wilk normality test at this value telling us that we have non-normal data sets. These are our residual plots. Given the line the data presents, it isn't particularly following the x-axis in any of the plots. As we can also see, our y-axis is very large, and especially for our fitted values, our residual plot is a little bit wonky. While the others tend to maintain a general form, this one you can see strings off several times. And for each of these plots, we can generally see the non-constant variance. In the beginning, you see that the points are more spread out, and the further you go on the right of the x-axis, they condense, and it is not an even distribution throughout the x-axis, giving us our non-normality. So our QQ plot, it fits the line relatively well, but as you can see, our y-axis is once again blown up. And so we had some work to do there. And for our added variable plots, we have some flat lines indicating that there's no real additional information you can get from these variables. We have some diagonals showing that these could be fairly helpful, especially on the bottom row. We had some of those, as well as the top. There are some slight diagonals. And the curved lines may or may not be helpful. If they are, it's not linearly. And as we can see, we have mostly those, particularly in the bottom row and on the leftmost column. So for our influence plot, we had data point 4, but it's not too far off. There's no major outliers, with the y-axis going from -3 to 3, and the y-hat only being at a 0.016 for that value. It wasn't too far off, and so we could rationally consider it not that much of an outlier. It wouldn't pull the data too far in any one direction. And so we did our transformation. This is for the box Cox. We got a multiple R squared of 0.9213 and adjusted R squared of 0.9208, which is lower than our original model. And so we went on to do the weighted least squares method, and that ended up being a lot better for us. As we can see on the top right, those aren't really the residuals that we want to see either. So we tried more methods. The ridge regression also didn't really go in our favor. As we can see, the y-axis is blown up once again, and the x-axis also is rather large. And so we got to the weighted least squares method, and this is the one that we really felt gave us the best model. We can see our R squared value at 0.979 and our adjusted R squared at 0.9789. Both of these are improvements over our original model. As we can see in the summary, we have p-values that are all below 0.05, with the exception of hospitalizations at 0.0668. However, in the ANOVA, they are all very much below 0.05. And so we reconducted our Brown-Forsyth and our Shapiro tests on this new model, as well as the QQ plot. And as we can see on the y-axis, our data is closer to being centered around 0. However, it does not follow the line any better than the original. And so although we're closer to 0, the y-axis is still very large, and it's not a satisfying result. As for the transformed residuals, the y-axis is much more condensed. And so we can assume that this data is much more accurate, as opposed to before, where the residuals were very large on the y-axis. These are very small. So although it is still not the best residual plots that we could hope for, they're not off by all that much. We can see that the non-constant variance has been somewhat accounted for on this plot. It doesn't look quite as varied as well as the normality. However, this is not the result that we got in from our revised Shapiro and Brown-Forsyth tests. Our p-value for the Shapiro is still 2.2 times 10 to the -16th, and our p-value for the Brown-Forsyth got even lower. And so these are not what we were hoping for, And as a matter of fact, the Brown-Forsyth test ended up giving us a worse result. For the added variable plot, these tend to fit the line more. There's some stronger impacts. As we can see, there's more diagonal lines. So that's what we're going for. Although most of them are still curved, the improvements on the diagonal is what we like to see. For our influence plot, we obviously have 0.914, in which we discovered a clerical error in our data. For that point, we had the age range of 5 to 11 being reported on for September 6th, 2021. That plot, that data point gave us a value for the age range of 5 to 11, 10,000 new cases that day and over 1,000 deaths. And because COVID-19 tends to affect children less than adults, especially the elderly, we can assume that 1,000 new deaths in an age range of 5 to 11 in one day is definitely an outlier and something that we had to account for. Then for our k-fold cross-validation, we can see that it got better with each variable. Step model 3 has the best one. As we can see, our RMSE is the lowest out of all of them. And so we can conclude that the more variables we included from our original set, the better. And so for our results, our weighted least squares summary and the ANOVA, all of our p-values are very low, although hospitalization is not statistically significant, as we can see in the summary at 0.0668. Although for ANOVA, we get 2.2 times 10 to the negative 16th. Let me go back for a second, I apologize. Our R squared and our R squared adjusted are both higher than our original model. And so we can say that this model is more accurate. And so for the results in our research questions, our F statistic value is greater than our F value, which means that we reject the null hypothesis and we can assume that age does have an impact on the vaccination rate. For our second question, our F statistic is greater than F once again, and we can say that the number of new COVID-19 cases does have an impact on the vaccination rate. For our third question, we also got that the F statistic was greater than the F value we got originally, and so we rejected the null and said that the deaths do have a linear impact on vaccinations over time. And for our fourth question, we once again got a test statistic greater than F, and our ANOVA p-value was much less than 0.05, and so we rejected the null, saying that the number of currently hospitalized people does have a linear impact on the vaccination rate over time. And so that is the end of our presentation. Thank you for watching.